Okay, so this actually is kind of like is a complement to A8. In A8, we looked at when we got a result of infinity and how that's a vertical asymptote. Here we're going to look at limits as x goes to infinity to help us find horizontal asymptotes. We're going to start out and kind of formally say this now. You are expected to know what these graphs look like. These are sometimes called parent functions. But these graphs, there's some expectation of you knowing what they look like and what some of these limits are. One that I think we're not always super familiar with, just because we really only started seeing it at the end of Algebra 2 and in function, is the graph of a logarithm. Does not matter what the base is, the graph always has the same general shape. Logarithms are not defined at 0. And they're not defined at 0 because as you approach 0 from the right, you get that limit goes to negative infinity. So that's our first limit there. There is an asymptote on a logarithm graph at x equals 0, and we are going to negative infinity there. What do I have to raise my base to get this really, really, really tiny number, right? If you're plugging like 0.1 into a logarithm function, you're saying, what am I raising this base to get 0.01? That's going to be a negative exponent, and the smaller your number goes, the bigger that exponent has to be. Every logarithm, no matter what base it is, has the point 1, 0 on it. It can actually be useful in making a sign chart too, because between 0 and 1, the logarithm is negative, and after 1, it's positive. What do I have to raise my base to get 1? That answer is always 0, no matter what the base is. That's what a logarithm does. I think logarithms are they're just tricky in general, but I always, whenever I haven't done a logarithm in a while, that's why I always ask my question. That's why I model that. It's a lot when I say, what's the log of this? I am asking a question. What do I have to raise my base to? So kind of why I model it that way. And then whatever that base is, that always has the point, that base, comma 1. I mean, because that's a silly question. Log base 7 of 7 is asking the question, what do I have to raise 7 to have a result of 7? That answer is 1. So those points are on every logarithm graph. You're expected to know that. The limit as x goes to infinity. Logarithms grow without bound. You can get as high of a value as you want out of a logarithm. So as x goes to infinity, there's no maximum. That's what it's saying. If you want to get a big number out of a logarithm, you need to use an even bigger number as your x value, but there is no limit to what you can do with a logarithm. Likewise, exponential functions. E to the x, most common, but really this fits for any base that you're using. Again, always assuming that your base is bigger than 1 here, because things are different when you're raising a fraction to an x power or doing a fractional log. Fractional logs end up just changing some of the rules around. This is another one. This is actually where what we do in the next section gets a little bit tricky, because things happen different on different sizes. As x goes to infinity, people overuse the term exponential growth. They'll use it to describe anything. But yeah, exponential growth. As x goes to infinity, your value of a to the x is also going to go to infinity. And you don't need a very big x value to get a really big x value out of an exponential function. Kind of the opposite of a logarithm. But yeah, so that limit holds. But on the left-hand side of base to the x, e to the x, you have an asymptote, right? And this line approaches what x value as you go further and further and further? 0. Yep, so as x goes to negative infinity, it's 0. The 2 points on this graph that you should know are just the same 2 points on the log graph, because the two things are inverses, but flipped. So raise any base to the 0 power, you'll get 1. Raise any base to the first power, and you'll get the base back. They're inverses. They're just opposite questions. So those 2 points are just flipped in x's and y's. You guys did that when you would find the inverses. You would change all the x's to y's and all the y's to x's. 1 over x in both directions. The thing that you should know what it looks like, and you should know these limits as x goes to infinity in both directions, and in both cases they go to 0. Yep. Take 1, divide it by a giant number, you're going to get a tiny decimal. If that decimal's not tiny enough, pick a bigger x value. All right. And then, of course, x to a power, even versus odd. The typo's been there for years. Even versus odd. You know, when you have an even, you get a U shape. I think this is probably x to the 4th. It's definitely not a parabola because it's so flat. The bigger your even power is, the flatter that gets, but it's still always the same shape. And in both directions, you go towards infinity because we're keeping our number positive. So it's infinity, infinity here. But with an odd exponent, your infinities match the infinity you're going to. Yeah, positive numbers will grow without bound positive. Negative numbers will grow without bound, but they'll be negative. And same idea, like this might be x to the 3rd. If it's x to the 5th, you're just going to get a flatter spot there. X to the 7th by itself will look the same. It's just the more you raise that power, the flatter it gets. So those are those are part of what you'll see when you start working on the review sheet, what I call must-know limits. That whole top of the review sheet with the must-know limits will have the same questions at the top of your test. Every test has one of those. Mostly every test has one of those, and they're designed to be free points. So when you look at your review sheet and you see the must-know limits, those are things that you have to just have cold. I think having the visual of the graph helps you remember those things, which is why I explained it that way. All right. Let's take a look at a couple limits where we've done a little bit more. We don't have e to the x, now we have e to the negative x. We don't just have x cubed, we have negative 4x cubed. Yeah, okay. And we'll kind of look at some techniques for doing these. We are going to do the same thing that we were doing with this first one, limit as e goes to the negative x, when we were talking about composite functions. E to the negative x is a composite function. I'm raising e to another function, and that function is negative x. It is great that x is going to infinity, but where is negative x going? So I'm going to rewrite this as limit as negative x goes to e to the negative x. If x is going to bigger and bigger and bigger positive numbers, where's negative x going to? Bigger and bigger, but negative number. Right? Yes, you're right. You're right saying smaller and smaller. That's the problem with the two types of small. But yeah. Also bigger and bigger numbers, but they have a negative sign in front of them, which is why it's correct to say smaller and smaller negative numbers. Yep. So that will be negative infinity. Which, of course, I can then rewrite as the limit as x goes to negative infinity of e to the x. I showed both steps there, right? Instead of just, I just felt with the infinity involved, it just seemed like showing both of them. So in the first step, I redefined the approach to match the argument, and then I just cleaned it up by making all of the arguments x. All of the negative x's x's, and that is a must-know limit from the top. As x goes to negative infinity, e to the x goes to 0. Yeah, even if you just went up and looked at it. It's this limit right here. Yep, cool. I don't know if I have a way to show this one, but I guess, yeah, I can actually, I know what I'll do. Yeah, I do have a way to show it. Sorry, I'm wrong. This is going to be equal to, because that -4 is a constant, -4 times the limit as x goes to -infinity of x cubed. This is the part that I cut out of E8. We didn't do one of those. And again, this is a must-know limit. That's an odd power. If I put giant negative numbers into x cubed, I'm going to get even gianter, because that's a word, numbers, but with negative signs in front of them. Which means that this limit is going to -infinity. But in the end, I'm going to multiply all those things by -4. So those numbers that were giant and negative, after they get multiplied by -4, are going to be positive, giant and positive. So this is positive infinity. So if you have a number being multiplied by your entire function, if that number is negative, it will change the sign of your infinity. Now, the thing about ln of x, ln of x is only defined for positive numbers. We talked about that in the continuity section. But here, we're doing the ln of x squared, which means that we're going to always have a positive number that we're plugging in. So we actually can find an overall limit here, but it does come down to looking left and right on this one. Because if we just tried to do it without looking left and right, we would have this. We would change x to x squared, right? And we can do that because as x goes to 0, x squared goes to 0, and then rewrite limit as x goes to 0 of ln x. But that limit doesn't exist because the function doesn't have a right limit as x goes to 0, right? But we're disciplined. We know what to do. Don't ever write does not exist until you've checked both sides of it. Limit as x goes to 0 left of ln of x squared equals the limit as x squared goes to 0, just like we said. But are those x squared values bigger or smaller than 0? If I plug a negative number that's close to 0 into x squared, what type of number do I get? Positive, which is bigger than 0. So x squared is actually going to 0 plus. Of ln of, hit that thing by accident, of ln of x squared. Which I can then just do my redefine and say equals limit as x goes to 0 plus of ln x, which is a must know, and it is -infinity. The ln function has a vertical asymptote at x equals 0 because on the right-hand side of it shoots down to negatives. But then we've done this before with x equals 0. We have ln of x squared. This should be plus. The same thing's going to happen when I plug positive numbers in. When I square them, they're going to be bigger than 0. So it's the exact same idea, limit as x squared goes to 0 plus. Which is exactly the limit we have written above. So without rewriting it, it's the exact same problem we've already solved. If I know that 2 plus 2 equals 4, I don't need to hold up 4 fingers to figure out 2 plus 2. I just know it. Same thought process there. I know what that limit is, so don't redo it. It's -infinity. Now just to show you all the things we've done before kind of still apply. B is a kind of loose way of using the limit rules, but it does work because you can think it through and it should make sense. Multiplying a limit that you know goes to -infinity by -4 is going to get you to positive infinity. Okay. All right. Just a minute time. That's 10:02, right? Is our time? Okay. I want to leave it on this. Okay, so we're going to find our first complicated limited infinity, and we're going to do it the long way, and then I'll introduce the short way, and my video tomorrow will finish off with the short way. The way to do these limits, if you have to show all the algebra, which you don't, is to find the highest power of x and multiply by 1 over that highest power of x, top and bottom. My highest power of x here is 2. So I'm going to multiply by 1 over x squared, 1 over x squared. We don't have to do this, but you should see it in case it shows up in like somewhere. Like, oh yeah, I know this is how it works behind the scenes, but it's much easier than this when all is said and done. You have to distribute that 1 over x squared to everything, which means that everything's going to be, you should be able to kind of cancel some of this in your head. The first thing we have to multiply is 3x squared times 1 over x squared, and those 3's are going to cancel to give us 3. Your next term is 4x over x squared, so you're going to end up with 4, but you didn't cancel all the x's out of the denominator. Minus 6 over x squared. Make sense? Yeah. All right, same thing in the bottom. You should end up with 4 over x minus 1 over x squared. Each one of those individual limits exists because you're dividing x by you're dividing a constant, with the exception of the 3, I should say. You are dividing the constant by a bigger and bigger number, which means you're going to 0, right? So all of these are in the same thought process as 1 over x. Divide 4 by 1,000,000, you're going to get a really, really tiny number. If it's not tiny enough for you, divide it by 1,000,000,000. If that's not tiny enough for you, divide it by 1,000,000,000,000. Here, you're just dividing it by that number squared. So same thought process. All of these guys go to 0. We end up with a 3 plus 0 over 0 minus 0. We've got a non-zero over 0 situation, right? So this is going to be does not exist, and we're going to leave it at that for the moment because I don't want to say the wrong thing. So this is going to does not exist, and that is because we're going to figure out the infinity in a minute, but I don't want to jump into that. I want to show the notation. Limit as x goes to infinity of 3 plus 4 over x minus 6 over x squared equals 3. And the limit as x goes to infinity of 4 over x minus 1 over x squared equals 0. Okay. Still have to figure out what infinity that is. It's not jumping out at me at the moment as to what technique I'm supposed to use to do that. So that's where I'll start the video out for tomorrow, which infinity that is. But I want to kind of introduce the easier way to do these problems. Most of our limits as x go to infinity are going to end up being fractions. And what we're going to be doing is we're going to be looking to see whether we have the same type of growth on the top and the bottom. Because if we have the same type of growth, that's going to give us a limit. If our top is growing faster than our bottom, that's going to give us to infinity, right? Because the top is growing faster, but the bottom's growing slower, so it's going to win. And if our bottom is growing faster than our top, then we're going to go to 0. That's kind of the 3 things that can sort of happen here. We have the same type of growth, we'll get a limit. We have bigger growth in the denominator, we'll get a limit, and that limit will be 0. The top is growing faster, it's going to win, and your graph is either going to shoot off into infinity or shoot down to negative infinity. And here is kind of the ranking chart of growth. Starting from the worst kind of growth, which is actually shrinking, to our fastest kind of growth, which is factorial. This is something that will not come into play until our last unit, but will come into play in a big way. So exponential growth when you have a negative exponent is not growth. I have that in here because you may mistake it. If you don't catch the negative exponent, you might have something that you think is down here. So this is not growth. A constant function is also not growth. The smallest general growth that we have is logarithmic. Like logarithmic functions do grow, but they grow very slowly. The bigger you make the x, the slower and slower the growth happens. That function sort of, go in the right direction, levels off rather than shoots up. But it does keep growing. And it does turn out that the smaller the base you have, the faster the growth is. So not that that really comes into play too much in logarithmic functions, but for completion, that line is there. After logarithmic growth, your next type of growth is polynomial. And this is one where you will have to know, the bigger the degree, the faster the growth. X cubed grows faster than x squared. Plugging a number into x cubed is going to get bigger and bigger and bigger than plugging a number into x squared is, right? Because you're multiplying 3 times. So with polynomials, you do need to look at the degree to see which one's growing faster. Exponential growth, we actually have a workaround for this, so it's not that big of a deal, but the bigger the base is, the faster you're going to grow. So 2 to the x doesn't grow as fast as 3 to the x, which should make sense because it's repeated multiplications of 2 versus repeated multiplications of 3. 3 is going to get you bigger faster, right? And then the fastest type of growth that we really are going to look at would be factorial growth, which is that, take a number and multiply it by 1 less than it, then 1 less than that, and repeat until you get down to 1. So like I said, these functions don't come up until, the last unit, but it's good to know it right now. So I'll start up there. I'm going to just revisit in my mind what I was missing from my mind for that one. We will do some really simple examples of deciding which the growth is, and then we will look at how we can use that to not have to do all of the work that I did in that example up at the top. From there, we will also look at horizontal asymptotes. So yeah, it'll be a decent sized video because this is a pretty big section. So yeah, cool. Yeah, I might skip over example 6. All right.